A study of a new mathematics teaching methodology tests students' ability to solve word problems. They're comparing the traditional, shows how the students using the new method, traditional method performed. And it asks us to identify the null and alternative hypotheses. The big one you want to look for is the alternative hypothesis. The alternative hypothesis is the one the researchers are really trying to test. Like, what's this whole thing about? And I'm not super excited about how they worded this question because they should be really clear with students one way or the other. They didn't say that they're testing to see if it's going to improve their ability, or if it's going to make their ability worse. So there's a bit of vagueness to this problem. Let's assume that they're testing to see that the new method is improving the scores. In other words, that the mean of the new method is greater than the mean of the traditional method. That's their big hypothesis. So that means that if you were to subtract the new method by the traditional method, it would be greater than 0, right? Because you could rearrange this inequality and it would say the mean of the new method is greater than the mean of the traditional method. And now, the reason why I said that at the beginning is because it doesn't explicitly say that. It's implied here, but it doesn't say that that's what they're trying to test. The only other thing I could think could be our alternative hypothesis is this one, that the two means are not equal to 0. In other words, that means there's some sort of difference. It could be that the new method is worse or that the new method is better. But I assume that they think the new method's going to increase scores. Look, I didn't even talk about H sub 0, okay? Because when you're trying to decide on a null and alternative hypothesis, the alternative actually needs to be decided on first. That's what you're trying to test. And the null method is like the null. Oops, so it's saying I'm wrong. It probably wanted this one. I guess I could have looked at their explanation there. But, without clearly saying that, we don't know what their alternative hypothesis is. So for this question, they should have said that they're testing to see whether there's a difference between the new method and the traditional method. Okay, so now we're asked to compute a test statistic. So this type of test is called a comparison of two independent means. Okay, because look, this new method, it has a mean of 57.7. This traditional method has a mean of 53.8. The new method looks better. It looks like there's a difference, but now we've got to do the statistical work behind the scenes to see whether it's a big enough difference to say the new method is actually better. Because it could be that we just got unlucky or lucky, depending on how you look at it, and the new method just happened to have a couple of students that performed above average just by random chance. So we're testing two independent means. They're independent. We're using the word independent because the new method and the traditional method are two totally different populations. You would call them dependent means, where you'd have a paired t-test. That would be a situation where you had like one kid takes a test, receives this new instruction on word problems, then takes the test again because it's the same kid testing twice. So this is the independent method. So we need this test statistic, and it's just like all of our other test statistics in a statistics course, where you calculate the parameter that you're interested in, and you usually subtract it by a mean, but this time we're comparing it to 0. So it was the mean of the new method. I forgot what they called that. M sub n. I don't remember if that was the letter. Subtracted by the mean of the traditional method. And then we want to see if that difference is comparable to 0. You don't actually have to put that minus 0 part if you don't want, because subtracted by 0 doesn't affect the calculation. And then the standard error is going to be the standard deviation of the first group squared, so that, in other words, the variance of the first group divided by n sub 1, plus the standard deviation of the second group squared divided by n sub 2. So if you plug all that information in here, except we're using a sample mean, not a population mean, in the numerator we're going to have 57.7 subtracted by 53.8, and that's being divided by the square root of the first sample standard deviation squared over 322 plus the second standard deviation squared over 269. And then if you simplify that, like I'm going to do 31.8 squared first. Then we're going to divide that by 322. So this decimal number is my first term inside that square root. And then the second decimal number inside that square root, 28.2 squared, divided by 269. Going to round that up to 3. Okay, so that's inside a square root in the denominator still. And then the numerator, I got 57.7 subtracted by 53.8, so that's 3.9. Okay, so if we simplify, take a square root. This is the denominator. I'm going to copy that to my clipboard because it's the numerator divided by the denominator. So 1.58 is what I got for a test statistic. Okay, that's our test statistic for this problem. Trying to think what comes next in the problem. Maybe I can pull it back up. They want the p-value for the test. So t equals 0 is in the center of the approximately normal distribution that we have for our study. 1.58 is somewhere over here. The p-value is the area that's in the tails from your hypothesis statement. Remember the beginning where I got frustrated because it doesn't clearly say whether they want a one-tailed or two-tailed test. Well, they said two-tailed, so the area inside these tails is the p-value. So what we want to do is we want to translate this 1.58 p-score into a right-tailed probability, and then we're going to actually have to double it to find the p-value for this problem. Okay, so to make that happen, what you actually have to do is use some sort of technology to convert the t-value we have of 1.58 to a right-tailed probability. So every t-value needs to have a corresponding degrees of freedom. And for an independent means test, like the one that we have, I shouldn't use the word pair. If the independent means test, for the difference of independent means, we have to use this degrees of freedom formula. And it stinks. Here, maybe I can find something online, but Excel just doesn't have something where you can just say, here are my two numbers, and here's my standard deviations, tell me what the degrees of freedom are. That's not built into Excel, but maybe there's some technology online. I found one, so if you want to pause this video and type this in, it looks like this calculator is going to give us the degrees of freedom without us having to use this formula by hand. So if you go to that website, after you pause the video, type that address in, it should look something like this. And we want two sample with unequal variances, like we said at the beginning. And then they just want you to punch in your summary statistics, but notice they're looking for variance here too. So my sample sizes are 322 and 269. 322 and 269. My variance, well, I have my standard deviation, so my variance is just the square of the standard deviation. So for the first group, it's 1,011 and 24. 1011.24, and then for the second group, my standard deviation is 28.2, so that's 795.24. What do we have to click now? There's so many buttons. Send this result? I don't know. No. Maybe it's already done it somewhere, I just don't see it. Oh no, I hit refresh, I lost it all. And then the other one was 1011.24, and then the sample sizes were 322 and 269. There's no button. I just want to push a button to calculate it. Let's try send this result, and I'll just copy that link and paste it in my web browser. Oh, it was right there, huh? I think it was right underneath this here. So get this out. Yeah, it was right there. 586.9 is our degrees of freedom. Okay, so we need to know that degrees. Now we can at least, we don't have to do that whole formula. 586.9 is our degrees of freedom. And so now we can take that t value of 1.58 and that degrees of freedom, and we can go to another online calculator, or actually let's use Excel, since we're trying to use Excel as much as we can here. If you find an empty cell inside Excel, type equals, type t.dist, and then it shows you some options. Remember, ours is a two-tailed test, so you can save yourself some trouble down the road and choose the two-tailed t-distribution. What this function does is it spits out a tailed probability based on your t value that you got. So in this problem, I got a t value of 1.58. So I'm going to plug 1.58 in here for the first part, and I'm going to put a comma, and then it says degrees of freedom come next, 586.9 for my degrees of freedom. .9. Okay, I got it all plugged in. So there's my p-value, 0.1146, because remember that's a two-tailed probability that we just calculated, which is what we wanted because we had a two-tailed test. So that's our p-value when we round it. And then to state a conclusion, you need to know what the significance level is, because that's what you compare your p-value to. So 0.01 is the significance level. Your p-value has to be below that number in order for you to say, hey, I've got some evidence here. I'm going to reject the null in favor of the alternative. The p-value is above, so we fail to reject the null. So it's either one of these two, fail to reject the null. And when you fail to reject the null, it means you don't have sufficient evidence. There is not sufficient evidence to say that there's a difference between those two groups.